So we're here today to basically commemorate the life and career of John Covey. Long career John Covey had, over 40 years, I believe. And we have some special guests. We have Marlon Scully from Texas A&M and Wolfgang Streich from the University of Ulm here visiting. And they wanted to do a presentation and talk about Marlin during this commemorative colloquium. And sort of the schedule is they will speak first, and then we'll save some time later, and I will invite various people to come up and say a few words about their experiences with Don during his long career here at North Texas, or anywhere else in the world that he visited with them. And then after which we have a reception, which everybody's invited to. It's just across the atrium in the exhibit center, where we can spend some more personal time visiting with Sonia, visiting with each other, and just celebrating the life of Don Covey. If Sonia's actually not going to give a presentation, but she wrote a document here which you can pick up. I think I'll just pass out for those who didn't come in. Some of you already have these. But I think because of the time, we ought to get started to give Dr. Streich and Scully their time. So, Wolfgang, please.
So, Chris, many thanks for the kind introduction. And let me start by greeting Sonia. It's a great, how would I say this, great honor for me to be here and give a speech on behalf of Don. You might say, well, how long has Streich known Don? 5 years, 10 years? And the truth is, I met him in the summer of 1983. Why did I meet him? Because he had written a paper together with a guy named Yang on gauge invariance in quantum mechanics. Now, gauge invariance in quantum mechanics is a very old topic, dates back to Hermann Weyl, and you will see this paper in a more formal talk later on. But there was a question that came up with the Nobel Prize work of Willis Lamb in 1947, the so-called Lamb shift. And in this particular paper, there was an interesting remark, a footnote, in which Lamb had said, if I would have calculated this shift of the energy levels in the direction of P dot A, I would have not gotten the right answer. I have to take the dipole times the electric field as the interaction between the light and the matter. And that was in a footnote. And many people have worried about it. And as I said, Don had written a very impressive paper, and it got into the hands of Marlin. Marlin, of course, being a student of Willis Lamb, had heard a lot about this question of E dot R versus A dot P. And Marlin said we should have a conference on this topic. And Marlin put together this meeting in Wyoming, and people, the future Nobel Prize winner Claude Contanucci was there, Ivo Bienitzki, Berula, the top people in this field. And Don gave his presentation on this paper, and this is how I met him. Then for many years our paths did not cross till I moved here partly to Texas A&M, up to Texas A&M, you can see that up here already, but to Denton, to have a house here and to relax from the work in Germany. And suddenly I get a phone call from Don Covey, and he says, look, I've heard that you are here in Denton. Why don't you come and spend some time with us here in the physics department? And this was more than 10 years ago. And since this time, Don and I have quite often talked about various parts of physics. And the latest, the last, and lasting, I think, collaboration with him was on the topic that Marlon and I will talk about in the more scientific part as we go along. Don visited us in Ulm You see on the left-hand side a picture of the view from our university. In the front is the church tower, the highest church tower in the world, 163 meters. In the back you see the famous Basilica of St. Wiblingen. It's a monastery, about 900 years old. And of course in the back you see the Bavarian Alps. And of course that's only about 100 kilometers away from us. I also have now a second home, Texas A&M University. And if I would have a pointer, I could even show you the physics department on that particular map. So what I would like to do now is tell you a little bit about the life of Don Kobe. Of course, most of you know him very well, have known him very well, but maybe you don't know about his scientific career and where he came from. And then I will hand over to Marlon, and he will prepare the scientific collaboration that we have had and outline them. This is the stone over in the graveyard of Don. And two things impressed me when I took the picture in the January together with Sonia. We went there. And what really impressed me were two things. The remark, "I love you, Sonia." I think nothing could be more true than that. And the Psalm 19.1-2. And I looked it up, and oh, thank you so much, that's great. I looked it up, and there it is. And I cannot read this to you, only partly, and you will see this in a minute. The heavens declare the glory of God, and the firmament shewish his handiwork. See? I knew that this. Sam, can you read it for me?
And show it the same way.
I see. Today unto day.
Uttereth.
Aha. Speech, and the night unto night.
Showeth.
Showeth knowledge. So, now why did I choose a sentence that I couldn't even pronounce? Because this was on the announcement of Don's death. Not the new version that I could have pronounced, but that particular one. So last night, Sam, we were debating about it. Should I take it out and replace it with a modern version? And Marlon said, no way. This is the original one. Then if English was good enough for Jesus, it's certainly good enough for us. So here is an excerpt from Don's resume that I have received from Chris Littler. He was born, as you could see, in 34, January 13th. And one thing I only found by accident, he was born in Seattle. You could not find this in the resume, so I found it recently by accident in Seattle. In 1956, he got a bachelor degree in chemical engineering at UT Austin, and his first papers were even in this field. He published together with his brother, if I understand correctly, because there are two papers by Kobe and Kobe, and they sound very...
His father.
Oh, his father, see? So I was very impressed, Kobe and Kobe. And then he did his master's in physics at the University of Minnesota. And then in '61, his PhD at the University of Minnesota. And 61. Now, he was from 68 to 2008 associate professor here. And from 2009 till 2011, Professor Emeritus. Now you see, this is the 40-year career that Chris was talking about here in Denver. What I really found impressive was the places that he had been before he came here. Remember, in '61 he got his degree and he spent 2 years at Ohio State University. From '63 to '64, he was Fulbright lecturer in Taiwan, Taipei. He was from '64 to '66 at the University of Uppsala. From '66 to '67 at the University of Copenhagen, and from '67 to '68 at Northeastern University in Boston. So here's a man who really has traveled around and seen many departments before he came here and brought all of his experience to this place. 140 publications and referee journal books, chapters, and conference proceedings, and Of course, he had a deep belief in religion. Here is something I got from Sonia, a poem from Franz von Assisi, if I remember correctly. And it's in his handwriting. And of course, I'm not going to read it all to you. But you see, it starts with the word Lord. Now, religion played a very important role in his life. Now, I showed you 140 publications in science, and there is this paper that Sonia gave me while I was here in January of '98, where Don published in the American Journal of Physics an article about Copernicus and Martin Luther, an encounter between science and religion. And it's a really fascinating paper to look at. Why is it? I was not aware that Martin Luther, once he became famous, had a lot of groupies. Today we would call them groupies. And they were sitting there at his lunch table and his dinner table, and they were taking notes. Every word that Luther said was written down immediately and distributed. And so one day, obviously, somebody asked him about Copernicus. And he made an off-the-cuff remark about Copernicus, and immediately it came into the annals that Luther doesn't like Copernicus and his point of view of the world. And it was interesting that really now, Don went through the history books and various letters and literature that he could find and showed that it's really not true that Luther was against it. It was just, people caught him in a moment, and he made a remark, and the microphone was on in some sense. And so, as for this reason, he came down in history, and it was Don who really put this straight in the record, so to speak. So, what we will do later on is, of course, talk about this paper that we wrote with Don, and it was really triggered, and I will say a few words more later on. This paper was really triggered by Don, and he has contributed immensely. And this is not the only paper. 2 more papers we have been working on the same topic are not in press yet, not even submitted, but exist and will be submitted soon. And with this, I want to hand over to Marlon, who is going to make more personal remarks and then, so to speak, prepare the scientific section on the Schrödinger equation that we want to talk. So, please,
Thank you, Wolfgang. We're keeping careful track of the time. The point being that we'd like to leave time for people who want to share comments and remembrances about Don. So I'm going to continue with some of these memorabilia. Don was a great guy. I loved him from the first time I saw him. He was a Christian brother, a fantastic physicist. No matter what problem I would come up here from College Station or wherever and be interested in, Bose condensation, gauge transformations, no matter what it was, Don had thought about it and written an interesting paper. And it was just great fun to be around him because he was always so interested in what you were doing. And that's a trick, by the way, for you students. One of the things you should do is become interested in what other people are doing, especially your boss. Don was always naturally interested, and he has several letters. We have collected several letters from his friends and his students, and one of his students, our friend here, Sonia, help me out. Who's this?
Miguel.
Yeah, Michele
Miguel, but his last name is Campisi, right?
Yep.
So Campisi writes that I'm sorry he couldn't be here, and without Don, it is quite likely that I would have dropped out of science. And he mentioned in his letter that he particularly appreciated the Thanksgiving. You begin to see why we like PowerPoint, right? I had some of these old pictures from the UGA presentation. But he was interested in statistical mechanics and went to Ulm, gave a seminar in Wolfgang's group at the request of Hange, and then went to Professor Hange in Augsburg. and did a postdoc there, and has continued on. Another of Don's students who you remember, Sonia? Who's this?
Another spot cheek.
Okay. And he was a successful scholar in a couple of dimensions, but I'm going to skip ahead and mention Don's favorite collaborator, his most successful collaboration, as we're all proud to know Sonia and glad that she was such a positive increment in Don's life, because without you, he couldn't have published as many papers. Now, we're going to talk about Kobe Schrödinger et al. But in particular, you may not realize that Schrödinger himself was a bit of a mystic. He was a very deep thinker, and you know, of course, that not only did he invent quantum mechanics, not only did he give us some of the deepest insights into modern physics, but he was also the turning point, he was also the instigator of the work in biology which put Watson and Crick onto DNA, onto the molecular code. Here are some of his remarks which Don and I appreciate. I did never talk this over with Don, but I know he would have liked it. Some of the most, as Schrödinger said, some of the most interesting questions. Who are we really? I say the most appreciable help science has offered is in the gradual idealization of time. There are several ways to look at the concept of time, and in particular, Plato was the first to envision the idea of timeless existence and to realize that the idea, the form, is in an interesting sense more real than the experience. And in the view of Schrödinger, statistical time, entropy is time zero. We're looking at the way in which time can be viewed as a mixture of many, many little events, taking them all together in a coarse-grained sense. And it's Schrödinger's point of view that statistical time has an even stronger bearing on the philosophy of time than the theory of relativity. I assert that the physical theory in this present stage strongly suggests the indestructibility of mind by time. Fascinating idea, and one that Don and I completely agree with. Turning now to the Schrödinger perspective, you remember from your course in quantum mechanics, right, Sonia? You took Don's lectures. Little joke there. You remember that Schrödinger, from on high, more or less, handed down his famous wave equation, where psi is the quantity, the wave function, the state function, which represents everything. And he writes down this funny equation. And for the graduate students in physics, you indeed recognize that it doesn't look like a wave equation. It has a second derivative in space, that's good, but it has a first derivative in time, and that's very strange. But not so strange if you remember Hamilton-Jacobi theory. Remember that energy is the partial of the action with respect to time, and momentum, p squared, is the partial of the action with respect to space. But let's not skip ahead quickly. Let's talk about the concept of action in advanced dynamics. In particular, I recommend this beautiful lecture by Feynman, in which he says that he's going to tell us about the principle of least action. And he came upon this idea when he was still in high school. And he was looking kind of bored one day, and his teacher, Mr. Bader, not Mr. Bader, comes to him and says, "Here's something really interesting, Feynman. if you want to calculate the time that it takes for a particle to go between 2 points, characterized by the time t1 and the final time t2, there is always some path which is the optimal path in the sense that the quantity that you're going to calculate is always the biggest for that path. Very interesting. And he goes on to explain that the laws of Newton can be explained in terms of this quantity, which is indeed the action. Keeping an eye on the clock, remember, we just talk to Wolfgang, but remind you that the action is the kinetic energy minus the potential energy integrated over time. This kinetic minus potential energy is, of course, the Lagrangian. And that, in my last view graph and my first blinding view graph, never put more than 1 or 2 equations on a view graph. You can't understand it, that's okay, nobody else does either. It always gives people a chance to check their email. What you remember is that it's the action S that counts, and in particular, that classical mechanics, coming up from Newton into the era of the 19th century with Hamilton and Jacobi, was very close to quantum mechanics, very close. And it's in this sense that we are interested in understanding the Schrödinger equation better and better, and in this sense that Don wrote his last paper on the subject of the Schrödinger equation. And since we're fortunate enough to have Wolfgang here with us again today, I'm going to turn things back over to him and let him tell you about this PNAS paper, Proceedings of the National Academy of Science paper, how Schrödinger can be understood from the point of view of the Hamilton-Jacobi theory.
Now I need to press again to turn on the talk, and I will use the time to give credit, and I have to really say that the paper was really triggered by Don. I came to visit a couple of years ago, and Don showed me a paper that he was working on, preparing, and he said, look, there's something interesting about the Schrödinger equation. And I said, nah, there can't be, people have thought so much about the equation that it came from. He said, no, I think there is something. So he got me interested. And then I got Danny Greenberger interested, and I got Marlin interested. And of course, in the end, the paper didn't look like anything that we had originally. But I have to say, without Don, certainly none of us would have worked on this problem. So, let me give you a very brief history into the history, a brief history of the Schrödinger equation, and then about the center of that particular paper. And then I will show you, namely this mathematical identity, and then I will show you what is really the crucial difference between classical statistical mechanics and the Schrödinger wave function. So the whole thing started out by this particular paper by Schrödinger, Quantization as an Eigenvalue Problem, 1926. Some of you might recall why this paper was even written. There was Louis de Broglie, who had published his thesis on the idea that there would be matter waves. And Schrödinger at that time was a professor at the University in Zurich. And the big boss at the ETH in Zurich was Peter Debye. And Peter Debye was in charge of the colloquium in Zurich. And he said to Schrödinger, well, Schrödinger, you don't do anything useful right now anyways. Why don't you prepare a colloquium about that thesis of de Broglie? And Schrödinger was the junior professor, so to speak, and so he had to do it. He did it. And after the colloquium, Debye said, hey, if that's true what de Broglie says, there must be a wave equation for these matter waves. Why don't you spend the summer deriving this wave equation? And so Schrödinger went out there to a little village in the Alps in Austria. The town is called Alpbach. Met a 16-year-old girl and was very busy in many ways and wrote all these papers. There were about 8 of them that he wrote within a couple of months. It was just unbelievable how productive the man was with his 16-year-old girl. And this is the very first communication, and you see right away he starts out with what we call the Hamilton-Jacobi equation. Energy is the Hamiltonian, and we replace the momentum by the derivative of the action with respect to position, exactly the way as Marlin had talked about, the action being the integral of the energy, of the potential energy, kinetic energy minus potential integrated over time. And then he made a substitution in this equation, S equal to the logarithm of this function psi, which when substituted into here gives you a rather complicated equation, namely this particular equation here, where you see the square of the wave function, the first derivative appears, and I would rather say the gradient of psi squared appears. And here is the Coulomb potential. Now, of course, he didn't like anything like this in the equation's nonlinear terms, so he said, let's take a variational principle in which we minimize the wave function psi such that this action, this variation remains 0, and this led him to this equation, which today we call the time-independent Schrödinger equation. And then he found for that, because of the Coulomb potential here, he found that the energy eigenstates, as we would call it today, give you the Balmer series that was known, of course, much earlier, and of course from the Bohr theory. There was an agreement, provided you would choose this constant that appeared here to be related to Planck's constant. So the big result of that first paper was that you can write down a kind of wave equation as Debye wanted and get the energy levels of the hydrogen atom. However, there was no time dependence in this equation, and of course you wanted to understand, if you shine light onto an atom, why is this atom absorbing that light? How is that process, how can that be understood? So you needed some time dependence, and this is now the fourth paper in this series. And as I said, I can show you the dates. They really were submitted within months from each other. And now he writes down a new equation that, of course, always has to go back to this equation, because that he believed in deeply, because it showed the energy spectrum of the hydrogen atom that was known. But here now appears a second derivative, and here is the first derivative. But the energy, as you can tell, here enters in a funny way. Here's E squared. Now, he played around with this equation a lot, and then he says, okay, let's write this psi as a phase factor, and then we get this equation again. Now here is E squared, he doesn't like that. Then he squares the whole equation to get this equation here, which has now here the second derivative squared, so that you can really get the fourth derivative. So this is a differential equation of the fourth order. And so he plays around with all these equations, and he's arguing, and then in the next page he suddenly says, well, that's what we're going to do. We're going to take the psi dt equal to this E times psi, and then we're going to end up with this equation, and that's it. So this is how the Schrödinger equation was derived by Schrödinger. It was a trial and error. He took this equation, it didn't look like this equation, it didn't look nice. Maybe I can solve it. And then he says, here's an equation I can solve, and it looks simple, and that's what we're going to take. So there is no real motivation, no derivation behind it. Now, Marlin pointed out the appearance of the imaginary unit in this equation, the I that appears in there. And you might say, why is it that the I appears there, and why is it that Schrödinger put the I into quantum mechanics, the imaginary unit? And this goes back to Hermann Weyl, and something which is, the paper was called Gravitation and Electricity. Hermann Weyl had the idea that you could derive, and you notice the dates here are somewhere 1918. Why is this important? because in 1916 Einstein had published his theory of general relativity, and that was based on parallel transport, mathematical tools. You take a vector, transport it along some line, and then you see when you come back at the original point, this vector might have changed its orientation. And when has it changed its orientation? When there was curvature in space and time. And this is one way of deriving the Einstein field equations from the parallel transport of a vector. And now Hermann-Weyl said, well, maybe we can also not only allow the direction to change, but also the length of the vector to change. And then we have 1 degree of freedom more, and we can derive the electromagnetic field. Now Schrödinger, and this is depicted here, we take this vector, transport it along a sphere, for example, which expresses the curvature, bring it back, and you see the orientation of these two vectors have changed. But not only this, the length has changed, and the length scale change brings in an extra field. And you see there's the electromagnetic charge is involved, a constant is involved, and an integral of the transport of that vector along the line. Now, Schrödinger in 1922, and please note, the other papers were in 26. So in 22, Schrödinger, already in Zurich, said, let's take this factor of Hermann-Weyl and put in the problem of a hydrogen atom and calculate this factor for the hydrogen atom. Why? What would we see? He sees, well, it turns out that for the hydrogen atom with the Bohr model, not with anything fancy as a Schrödinger equation, just the Bohr atom, we will find that this is an integer multiple of 2 pi h bar. And then he said, gee, then maybe this constant gamma that nobody knew what it would be is related to h bar, and maybe one should involve the square root of -1, namely the imaginary unit, because then this is not really a length scale that is changed, but we just accumulate a phase factor and nothing magic happens. As we go around and transport this vector, we come back to the original point, and all we have done is picked up a phase. So this is in this particular paper. Now you understand why Schrödinger was inclined to put in an I into his equations, because 4 years earlier he had that already. So let me now come to the central idea of the paper with Don, and as I said, it's emphasized that it started all out with Don, and Danny Greenberger and Marlin helped us on this. And the central idea is a mathematical identity of complex numbers. So if you take a complex number, and it's not just a number, it's a field. It's a field of complex numbers that depend on the position and time, and they have an amplitude and a phase. And if you now differentiate this at appropriate times, you're going to be able to derive this identity. So on the left-hand side, you see the first derivative of that field with respect to time. You see the second derivative, the Laplacian, of that field with respect to position. And then this can be written in terms of amplitudes and of these phases in this particular way. This is a thing you can easily derive. You just have to, so to speak, see what you're looking for. Now, why is this interesting? Now, here is the equation that Marlin was talking about, the Hamilton-Jacobi equation, where we take this classical action with respect to time and set it equal to the gradient, the momentum, so to speak, of that field, plus the potential. And it turns out that Van Vleck in 1928 already found that if you now have not just a single particle, but an ensemble of particles, whose phases you don't know exactly, but you know the energy, namely, you could write such an equation, then there is a continuity equation for what we call today the Van Vleck determinant. Namely, you take this action that is determined in its time evolution by this equation and differentiate it with respect to the coordinates and the integration constants of this equation. Take the determinant of this quantity then you will see that it satisfies this continuity equation. So now we have done an important step. We have gone from an individual particle to an ensemble of particles with random phases. And these particles satisfy two equations. This equation, and you look at this D, what is this von Fleck determinant? I showed you that it can be calculated in this particular way, but it satisfies a continuity equation, therefore it is a density. It's the density of particles in this particular configuration, and this here is the velocity of these particles. So this is a field theoretical description of classical statistical mechanics. And if we now remind ourselves of this mathematical identity that I showed you, then you see this term and this term are part of this Hamilton-Jacobi equation, provided that phase is the action divided by h bar. This part back here is identical to this part, which is the continuity equation. As a result, if I define a wave, which would be the square root of that density times e to the I over h bar s, with an appropriate definition of this constant beta here, then you will see that these terms simplify, and this term simplifies, and what I find is this particular equation, where Q is the second derivative of the absolute value of that wave divided by the absolute value. So this equation was derived for the first time in 1963 by Professor Schiller, and then in 64 and 86 from a different point of view by Nathan Rosen. That's the same Rosen that did the Einstein-Podolsky-Rosen discussion many years earlier. Now, why is this equation remarkable? You notice that the first two terms are the terms out of the Schrödinger equation. The third term back here is what we would call the Bohm potential, the quantum potential. But usually, the Bohm potential does not appear in the Schrödinger equation. It appears in the phase equation rather than the wave equation. Now, it's because of this h bar squared here that this equation is not really a quantum equation. This equation is a purely classical equation, despite the fact that h bar enters explicitly at two places. Why? This is just a fancy way of combining two classical equations so that in the end you have an equation that looks quantum, but in reality it is not, because the two underlying equations that we have started from are classical equations. And, most remarkably, if you go back, you'll see something interesting in this set of equations. What we have here is we start out, these are no h bar in this equation, no h bar in this equation, but in order to get the exponential dimensionless, you need to involve an h bar. Two things that are remarkable. You take the square root of the density here in order to find this wave. Why? You need to do this in order to get the a squared in this mathematical identity so that you can use this equation. Why is that? You remember the Born interpretation of quantum mechanics. Psi absolute value squared is the probability, or I should rather say the probability density, to find the particle at a given position. And now here, of course, there's not that much mystery left, because already classical statistical mechanics, then viewed in terms of a wave, experiences that. What? It experiences that you have to take the square root of the density to get a simple equation as a wave. Moreover, you see from this that the density is driven by the action, that is the phase, but you know that the phase equation is not driven by anything like the density. The density does not appear in this equation. So classical statistical mechanics has a symmetry breaking, of course not in the sense of particle physics of a symmetry breaking, but a breaking in the coupling between this equation and this equation. because this equation is determined by the outcome from here, but this equation is not determined by anything from here. And as a result of this asymmetry, the wave equation that Schiller and Rosen had found has this term, this Q term in it, which ensures that the underlying equations are independent of h bar, but they're also nonlinear because you see here the gradient of psi absolute value divided by psi absolute value. So now you might ask yourself, how do you get to the Schrödinger equation? And this is a very little step that we now have to do. We go back here and ask ourselves again, we take an amplitude, a phase, and as the underlying amplitude equation here, we take again this continuity equation, but now we take this quantum potential into the action, and what we find, of course, now is that we get a symmetric coupling between this equation and this equation. The amplitude of this wave is governed by the phase, and the phase itself, again, is governed by the amplitude. And as a result, this term that appears in the mathematical identity will now appear in the phase rather than the wave function, and the underlying equation is linear, because the nonlinearity has now been put not into the wave function, but into the phase. The chairman has gotten up, so let me just emphasize again, I'm almost finished here. What we see in this section here is the classical part, here the quantum part. Here you see this phase determines the density does not determine the evolution here. In the quantum case, it's a symmetric coupling, the amplitude is defined by the gradient of the phase. The phase in itself is determined by the amplitude. As a result of this combination, this symmetric coupling, we're going to get linear equations rather than nonlinear. So with this, I want to conclude, but not without showing you the two papers that we have been working on with Don that have not been submitted yet. Again, on the derivation of the Schrödinger equation, eliminating the remnants of classical mechanics and the emergence of the Schrödinger equation, and again on the linearity of quantum mechanics and the birth of the Schrödinger equation. With that, I thank you again very much. You'll see from these two transparencies that the influence of Don will go far beyond his life. And as Marlon always said to me once when I was a young man, you write a paper for 3 people. You write it for yourself, you write it for the referee, and you write it for somebody who is not born yet. And in that sense, Don's papers will really last on forever. Thank you, Marlon, and thank you for your
So Chris has organized a few remarks, and I'm sure Sam has a few more remarks. Where's Chris? We turn it over to you to orchestrate. You want me to help you?
Yeah,
I'm good at jumping up when somebody
I was
talks,
also
so they're just
thinking,
exactly there right
well, I
on
was
time.
there,
Wolfgang was right on time, by the
yeah,
way.
he was right on. Sonia had some pictures, which I think I can have scrolling in the background during the comments. Let's see if that works. And as I do that, I know of a few people who would like to come up and make some remarks, and then after they're done, then I'll open it up to the audience and have a few more if they would like to come up and say a few as well. And I'm trying to decide, should it be ladies first or? Of course. Yes, of course. So, okay. Ladies
What a
first.
good excuse.
Yeah.
I met Don Kobe 1977 I was an undergrad at the time, and he was notorious a hard professor. Took him, I remember the dipole times the electric field. Yes, that sounds like Don there from way back. He was notorious a hard student, hard professor. There was a student who came to me and said, you know, when I was advisor, and said, he's a good professor. So any of those things you hear as advisor, don't listen to them. He is a good professor. This student went on, Nicholas Lopez, to be a graduate student at the University of California, Riverside. But in Don's own words, found online is homework guidelines, students. Yes, and he wrote in this guidelines to his students, 14-10-20, physics 14-20, when you are employed, your employer will evaluate you on basis of the written work that you submit. It is extremely important to your future success that you begin now to develop good habits for your written work. For this reason, I am asking you to follow these guidelines for your homework. And there's a 15-step guideline. And he included a couple equations, including the electric field notations. So there you go. Don Kobe was my Christian brother and my colleague and my former professor. I was very inspired when I was first at UNT, and to hear as a person who liked to think on the things of faith and to think on the things of science, and that's a real treat to have as a professor and my professor. Sonia, I still remember his excitement when he told us about you, and it was another very big thrill to meet you and see you all together over those weeks. Thank you.
There was more to Don Kobe than met the eye. Indeed, there was a side of Don that many of you may not know very well. He was a man of science, but he was also a man of deep faith. And Don encouraged me time and time again, one who shares with him a faith in Jesus of Nazareth. It was Don who introduced me to the American Scientific Affiliation, the other ASA, not the Acoustical Society of America. These scientists are North American scientists who are particularly interested in the interface between science and the Christian faith. It was Don who almost insisted, dare I say, nagged me to become an active member in that group, and so I did. Recently, a mutual friend, Steve Pogue, shared a little story online, and I found it so apropos that I asked Steve if I could share it with you in a greeting. So, Steve writes, the son of an engineering professor, Don discovered his love for science in high school, where he was president of the Slide Rule Club. Steve asked him, Don, would you consider yourself to be a nerd? I don't know, but I was the president of the Slide Rule Club. But he also struggled with loneliness, wondering whether life had a purpose. He wondered where it was worth living, he once told Steve. In late high school, Don began reading the New Testament. I was very impressed with what Jesus said and did, John recounted. He decided to put his trust in Christ and grew in his faith. But going to college brought doubts about his new beliefs. The university course in philosophy, reading Bertrand Russell, nearly convinced him that agnosticism was the only truly intellectual position. Don is reported to have said, fortunately my philosophy professor gave very balanced lectures, he said, and he was introduced to the writings of C.S. Lewis. Reading Mere Christianity, a major work by C.S. Lewis, Don found his faith renewed. I began to realize that there are many compelling reasons to believe in God. I regained my faith, which was made stronger by my intellectual struggles, he said. Don would stay a bachelor until his 50s, and then I remember when he married Sonia, and whom he had met during his travels in Brazil. They lived in Denton until he retired. Then he divided his time between Texas and their native São Paulo, invariably always avoiding the snow, it seemed. Marriage made him a better prof, as we know. Don spoke on many campuses in the U.S. and abroad about the conflict between science and faith. He explained, science investigates the mechanism of nature, theology investigates the purpose of nature. Most of the present controversy between science and Christianity is a failure to recognize these distinctions, he recounted. I am confident that Don would, as he has done many times before, been an ardent supporter of the kind of symposium with the group here on campus that he belongs to, and I'll show you, give a plug. And I'm going to suggest to them that we actually dedicate the composer. Our colloquium speaker is giving us a twofer. One, he's going to be talking, this is Mike Strauss on April the 1st, April 1st, he'll be talking about the Higgs boson and its importance in science, but also in the evening he'll be giving a talk entitled God, Evidence from Modern Science. And so this is an area that Don would have really appreciated. Indeed, there was more to Don than met the eye. In trips to China, he carried a suitcase with false bottom so they could bring Bibles into the country for those who didn't like them during the time that was frowned upon. Though reserved, he was never afraid to tell others, inquiring students or colleagues about Christ, or students in China or Brazil when he was on Fulbright fellowships. It is, in my estimation, that Don had three great loves in his life, summarized by a trio of alliteration. He loved his Savior, he loved Sonia, and he loved his science. In particular, our shared passion for physics. We have lost a creative and perceptive colleague. I have lost a constant and abiding friend. We're all missing, perhaps more in the future than we realize now, for Don Covey. For in Don Covey there was more than met the eye. And passing time will only make us realize that more.
My name is Bill Morgan, and I teach an adult Bible study class at First Baptist Church, of which Sonia and Don were members for some 12 or 13 years. That's where I came with my association with he and Sonia. She asked me if I would speak to his Christian testimony, and I'll be happy to do that this afternoon. First of all, Don and I are brothers under the skin. He taught in the graduate school here at UNT. I taught for 2 years in the graduate school at Colorado State University in one of their extension departments. And so together we had many interesting discussions in the 12 or 13 years of the Bible study which we shared there at First Baptist. Subjects like creation and a young earth and the sin and fall of man and the Genesis flood. Now, we had some lively discussions with many of those. But we also had some that he contributed from the science field, him being from that persuasion, such as he had questions about the Big Bang Theory. And we talked about, the Hadron superconducting supercollider. And, of course, the God particle. Now, we had some really interesting discussions there. But the best way to describe Don Covey's Christian testimony was not what he said, but what he did. As you know, Don Covey and Sonia, for many years, had invited foreign students to their home for holiday meals because foreign students didn't have time or money to fly home to their celebration. I remember Sonia told me one time they had as many as 25 or 30 students in their home at one time. Now, how about that? And so, I remember one time he brought a young man to the class from one of his physics classes. I don't know but what we might not have seen his picture up here. He was either Israeli or Lebanese, something. Israeli? And he was seeking information about the gospel message. And during that lesson, he asked some very penetrating questions. I've no doubt the young man became a Christian soon thereafter if he wasn't already. And it was all through the influence of Don Covey. And so as a result, we see him in action. Well, then there's a humorous story that goes along with this. One afternoon when Don Covey was coming out of his office at the end of the day when UNT had already turned out for the holiday, and he came out into the hall and he found a foreign student there in the hall, wandering the hall. And he said, well, do you have a place to go for a holiday meal and for fellowship and food? He said, no, he didn't have a place like that. He said, well, why don't you come on over to the house? And we have some students that are going to be over there for the holiday meal. And said, you bring a plate, and we share the food, and we'll have good food and good fellowship. And so, sure enough, when Don opened the front door to welcome him, what did he have in his hand? His plate. Don said later, he said, I might have made a little clearer explanation. That's just exactly what I meant when I told him to bring a plate. So the idea was that they were nearly always there. You remember that verse of Scripture that says, Jesus said, I was a stranger and you took me in? Or you welcomed me? Isn't that a perfect testimony of what Jesus commanded for Don Kobe? And not only that, you might ask, well, Lord, when did we see that? When did we see you do that? You'd say, Jesus answered, do you remember? Inasmuch as you did it unto one of the least of these my brethren, you did it unto me. And you might go on and say, go ye and do likewise. A wonderful, beautiful testimony of Don Kobe. I considered him my friend, and I'm privileged to have known he and Sonia for those 12 or 13 years. Thank you.
We have a few more minutes. If somebody else, the visitors today or one of the students would like to make a comment or two, we have a few more minutes before we need to recess and then go to the door. Back.
I first met Don Kobe in the 1970s. He helped me both in science and sports, and more than any other professor. He reviewed all of the few manuscripts I got published, and many more executives than I had published. Even those I had published would have been much inferior to that. So he went far beyond the call of duty, helping me both in my coursework and in the work as a student of my own. No other professor ever helped me that much.
That really encapsulates my experience with Don Kobe, both as a student, which I was a student of his, as well as Kay, but Kay got to say most of what I would have said, so I'll leave some more time for somebody else. If anybody would like to make some, yes, Mark, sure.
I don't mind saying that Don made a tremendous impact on my life. And every word I've heard about him tonight, today, or whatever it is absolutely true. Absolutely true. He was just a fantastic person. One of a kind. And I just thank God that I got to know him. And I also learned something today, why I flunked physics.
Okay, there's nobody else. I'll turn it over to Marlon for some concluding remarks, and then I'll show you the way over to the refreshments.
I love what you said. I also thank God for Don Kobe.
Thank you.
He was a great guy. I'm not of the mindset that says I lost a great friend. I'm going to be denied the company of my great friend for a while. But Don, 4 words: faith, family, friends, and physics. That was Don Kobe. He's not with my physics anymore, but he's an example for all else that we can be in life, and I'm going to always appreciate and indeed miss him. What we're going to do now is move someplace else for barbecue, right?
Barbecue and refreshments. Yes.
But before we adjourn, I would like to take this opportunity, as we do when somebody gives a nice talk, to express our appreciation to Sonia for raising Don.
Oh, well, I have a lot of makeup on.
That's his.
But really, right after the war, they told us in our churches General MacArthur was begging for missionaries. So I wanted him to do that. But there's a long history on why that didn't work out.
6 courses.
Thesis, basically.
Oh, 6 courses, 4 courses.
Aprendi vai comer
That student that was talking about, that Don student, Boris also has got a PhD in philosophy.
Eu sigo isso, e aí disso você então o que já ouviu na ficha.
So he's the instructor in there. Oh, great. Hi. Get that on camera, Chris. This is a former student of Dr. Cady. What type of instructor was Dr. Cady?
1990s.
He was very nice.
I'll pass it on.
That's all you can say. He's camera shy.
You can say more.
I love Dr. Kobe. He was very sweet, very gentle, quiet man. We miss him.
He's waiting for me to say something.